Thank you for introducing me. My name's KARRAR ALOFARI from Michigan Tech University. This is part of my research, which is the theoretical part, using the fractional flow function to extrapolate trapped saturation in two-phase flow in porous media. The motivation behind this study is the importance of a trapped saturation in many applications, like in oil recovery. So they are injecting liquid and gas to produce oil. However, there is a lot of amount of liquid oils trapped in the porous media. Another example of the importance of two-phase flow in porous media is in a fuel cell. So water is produced at the cathode side, and this liquid blocking the pores, preventing reactants to reach the reaction sites. In both and many applications like surface and groundwater, other examples, capillarity is playing a role and a main factor for liquid holdup or trapping in the porous media. So the objective of this study is using a fractional flow function, including the viscous and capillarity effect, to study the immiscible displacement and estimating entrapped saturation. So before going to this model, some properties and concepts important to understand before going to the model. So porous media basically is a solid matrix with void space, and the main property which usually used to explain or to describe the porous media is the porosity, which is a void volume to the porous media volume. Another kind of, or another property which is also important to the porous media is the permeability. It represents the capacity of the porous media to allow fluid to flow through it. And it is considered a dynamic property, not like the porosity, because it is measured by applying, by injecting the fluid through the porous media and using Darcy equation as shown here. So the permeability, in case if we have single phase flow, it's considered absolute permeability, which is only related to the porous media structure and morphology. However, in case of two-phase flow, which is our study related, in this case, the permeability is not only related to the porous media structure and morphology, it's also related to the saturation. So as the liquid saturation increases, that's means there is more permeability to that liquid, which means that this permeability called effective permeability, which related to the porous media structure, morphology, and the phase saturation. The saturation, it is the volume taken by the phase to the total pore volume. So from this, we come to the first concept, which is important, and it is the input to the fractional flow function, which is the relative permeability. Relative permeability is the effective permeability to the absolute permeability. It is a factor used to study the permeability of multi-phase flow in porous media. The method that is used to study the relative permeability is, there are many methods to estimate it. However, the steady state method is the common one to estimate it, which is based on injecting fluids. In case of two-phase flow, two fluids at different fractions, starting from single phase for the phase one, then starting including the other phase and so on until ending with the other one. And using the Darcy equation and weighing the sample after each test, from which we can estimate the relative permeability for each phase. For example, here, I am showing here for the test here, when running the test, we can find the relative permeability for the phase here, which is 1, for the other one 0. When we go to other tests, for example, this one, more fraction from the red color phase, we can see here the permeability of this one reduced because more saturation from the other phase is included, and then we have more relative permeability for the other phase. The other concept, which is also important to the model, which is the capillary pressure. And the capillary pressure, basically capillary pressure is the combination of interfacial wettability and the geometry of the pore effect, which all combined in the Laplace equation here. We can see the surface tension as well as the geometry or the chemistry and the geometry. The common example to explain the capillarity is the capillary tube. Here, an example to the geometry effect. In the porous media also, we have same thing. So if we're looking into to the microstructure of the porous media, also we have pores. So in case of two-phase flow, so if the injected fluid is the wetting phase, we have the imbibition regime and the capillarity working in the same direction. And in case of drainage, the capillarity acting in the opposite direction. So we can see how the capillarity can affect the immiscible displacement, especially if we have a very low pressure drop. So the capillary pressure can be estimated in terms of saturation. This is an example that I made here. So in case if we have injecting here wetting fluid, the wetting fluid more likely go through the smaller spores because it is the radius is too small, then the capillary pressure too high. So we have this region, as this one filled, then it go to this one and so on. So you can see the capillary pressure reduced and more saturation included. That's mean the capillary pressure can be estimated in terms of saturation. Leverett is the first one who estimating the capillary pressure in terms of saturation, and he provide a correlation that can be used to extrapolate the capillary pressure for any porous media based on the porous media properties and the interfacial tension between the two immiscible fluid. At the end, J is the curvature for the pore size distribution, which can be used for any porous media. Two terms which also needed that to show the that we'll use to compare, which is capillary number and viscosity ratio. Capillary number represent the viscous to the capillarity effect, and viscosity ratio is the viscosity of injected to the displaced fluid, which usually used to study the pattern of two immiscible fluid in porous media based on the pattern of the wetted area. So fractional flow function, basically, it is derived based on Darcy equation and the flow rate of fraction, as well as including the capillary pressure at the interface. We're ending to the general equation which shown here. So the first term here represent the viscous, then capillarity, then gravity. What we care about the viscous and capillarity. However, in general, historically, they only care about the viscous effect. But in our case, since we are care about a very low flow rate, the capillarity playing a role and became the dominant force in the immiscible displacement. The capillary term here is, we can see the capillary pressure here is a spatial derivative. However, the correlation available is in terms of saturation. So in this study, we simplify this term by using the chair rule as shown here. So now we have the capillary pressure derivative to the saturation, but we still have this term. We found that this term can be simplified based on the length scale suggested by Medici and Allen. This length scale is equivalent to the interaction between the immiscible displacement properties with the two immiscible fluid, which ending with the capillary spatial derivative can be written in this form. With that, the fractional flow function can be become at the end as a function of saturation, because the relative permeability is here as a function of saturation, as well as the capillary pressure, and the remaining are properties constants. So in order to apply this equation, correlation for Brooks and Corey, as well as to Leverett function are applied, as well as to some properties related to the porous media and the two immiscible fluids. So when we are solving the equations, we can see here, the blue is the classical solution, or the one which only including the viscous. And as the flow rate decreases, we can see more deviation from the viscous effect, which means this area is the capillarity dominant region, and this is the viscous dominant region. And when we get the derivative, we can see part of the region which is where the capillarity is dominant, it's became negative. And this cannot be considered a solution in immiscible displacement. So if we look to the saturation, which means this is not a saturation, this is not a solution, which means this is part of the liquid which is held up in the porous media, and it's immobile liquid. So it's considered trapped saturation. When we extrapolating these saturations, we end with this curvatures. for both imbibition and drainage. So we found that experimentally these are equivalent, the theoretical curves are equivalent to the experimental data we found online. In terms of the capillarity, we can see as the capillary increase, the trap saturation until a critical point start decreasing, as we see her saying. Also for the viscosity ratio, as the viscosity, this is low viscosity ratio, high viscosity ratio and medium and low. And same thing we found in the experimental. Now we found, in order to apply this to porous media, we need to find the exact correlation and capillary pressure for that porous media.
So you have 2 minutes to conclude, please.
Yeah, thank you for letting me know. So these correlations, we found these correlations for relative permeabilities and capillary pressure are for Berea sandstone. When we apply them based on the constant mentioned in these studies, we obtain the theoretical solution based and compare it with the experimental. There is a good matching between the two kinds of Berea sandstone, and this model can be used efficiently and very simply to estimate the trap saturation. So the conclusion, this simple fractional flow function model can be used to identify the dominant forces, capillary or viscous force. It also can be applied for both cases, wetting or not wetting injected fluid, in other words, imbibition or drainage. And finally, it can predict the trap saturation of the displaced fluid in porous media with respect to the capillary number and the viscosity ratio. This work is supported by Department of Energy as well as to the HCED Iraq. Thank you very much, and please let me know if you have any question regarding this study.
Thank you very much, sir, for your very interesting presentation. Actually, what fluid you have used in this? Just a water, or you use some kind of oil?
Yeah, so it is a theoretical study, but we are validating, especially for this part, it is oil and water. So they are, as mentioned here, they are using water or oil. So what you need to know the porous media.
Because the viscosity is much different of the water and the oil as well. So this is the question. I mean, what kind of oil and how much is their viscosity, and because there is so many other parameters also need to be considered rather than only viscosity and porosity, right?
You are right. So in these studies, actually, they from study to study, they are just mentioning oil. Even the water, it is not water, it is a brine water. I just write water here.
It's a brine solution water, right?
Yes. And these properties from them different from study to study. So I brought these properties from these exact studies and put them here. You are right. So the viscosity, the surface tension between these two miscible fluids, you'll find them a little bit different from study to study.
Yeah, that's fine. Thank you very much, sir. It's really a lot of thermodynamics here. Thank you.
Thank you.
Because my work is also similar to this, so just part of this. But I'm working more to the bitumen viscosity and bitumen fluidity material.
Interesting.
Because bitumen has the more highly, it's very highly viscous material.
Yes.
So, yeah. Thank you, sir.
Thank you very much.